Okay, as we heard in the previous sections of this workshop, interference, of course, is a very important effect. But what we have heard is most related to the single annihilation or ATI or such kind of processes. This interference, in fact, in the double annihilation is not an easy problem. So I will show in this talk that there's still many debates about this effect. What I will talk include many works from the cooperation with many colleagues from different institutions, including Wuhan Institute of Physics and Mathematics, basically the Xiaojun News Group, and also from Shanxi University, Southwest Jiaotong University, also Wilhelm Baker from MBI in Berlin, and IOP, and also many colleagues of my institute. Okay, I will talk about the so it's 4 parts, background and the rescattering excitation with subsequent analysis process and some interference effect in the rescattering impact analysis process. And then finally, is a simple conclusion and perspective. Non-sequential double annihilation have been first observed, okay, almost 40 years ago. Experimentally, people found this NER of the double charged ion is much higher than the prediction of the single active electron prediction. Okay, then the mechanism of this process caused many debate in the first about 20 years until this Coulomb has a very powerful facility to measure the differential the observations. Here's the correlation distribution and the momentum distribution, which is measured by these Coulombs. With this measurement, and of course, with theoretical calculations and analysis, the mechanism of this process have been decided to be the rescattering, as shown in these cartoons. The electron tunnel annihilation, and then it will be accelerated, and it will be scattered with this ion. When the scattering energy of the electron is high enough, then the second electron will be directly analyzed by collision. On the other hand, if the returning energy of the electron is not large enough, then the second electron can be excited to excited states, and then it can be analyzed by the field. Of course, it can also happen when the return energy is higher than the analyzing potential of the second electron. Theoretically, we have 3 different treatment. TDSE, of course, is very exact, it's accurate, but it's hard to calculate. Quantum model, we need many approximations. So the semiclassical or classical model, now called the CTMC, have been developed and widely used in the analysis. In this semiclassical model or classical model, we treat the electron classically after annihilation, after tunneling. This CTMC method has gained great successes in the study of this non-sequential time annihilation process. For example, for the momentum distribution, it is in agreement with the experiment, and also for the iron yard of the double charged iron and the single charged iron. Here we observed this kind of typical knee structure in the iron yard, and in some cases, this semiclassical calculation can also quantitatively reproduce the experimental observation. For energy spectrum and correlated distribution, they can all be well reproduced by this classical or semiclassical model. Even for the elliptical correlation and the circular correlation, the semiclassical model or the classical model give a consistent result with the experiment. Recently, this model has also been applied to the wavelength dependence of the non-sequential double ionization. Most surprised, the fine structures observed in experiment in this electron correlation distribution can be reproduced by the semiclassical or classical model, and the analysis shows the effect of the electron-electron interaction and electron-ion Coulomb potential effect in this fine structure mechanism. So some people even think that quantum mechanics is not necessary in our analysis or understanding of this non-sequential double ionization. So what's beyond the semiclassical model? That means what can we observe quantum effect, interference effect in the double ionization process? There are some difficulties in the experiment. One is the focal average. This effect will largely smear out the subtle structures in the distributions. And one more effect is the null statistics in the Coulomb's measurement. For this coincide measurement, the statistics is quite low. So usually it's hard to have enough number of events to show these detailed structures. So what we expect in the non-sequential double ionization for this interference effect in the rescattering impact analysis process, ground and continuum states are involved. So we expect the interference will happen between the different trajectories for the reside channel, since excited states are involved. So there may be some interference between the channels. So at first, let's have a look at the effect in the reside channel. In 2008, Heidelberg group report this very interesting measurement for the argon. We can see that this distribution translates from the anti-correlation at low intensity and to anti-correlation when the intensity is increased. However, this phenomenon is absent for neon. So we use the quantum model to calculate this process, which is the third order expansion in the matrix expansion. The first one is the annihilation of the first electron, and the second one is the collision and excitation. And the third one is the annihilation of the second electron by the laser field. So when the electron is excited to different excited states, they will interference and to give some effect which can be maybe observed in the experiment. We consider the five channels different excited states for different intensities. These correlation distributions show state dependence and also intensity dependence. More important, they are all symmetric. So our calculation also show that these three channels play the most important roles. So we make coherent and incoherent sum of different channels. In this incoherent sum, they are still symmetric, but for coherent sum, it becomes asymmetry, and so some intensity tend to be anticorrelated to correlated. One more other effect is to be considered is the tabulation. The tabulation will lead to correlation, but when we consider both effects, we can see that this correlation distribution shows a transition from the anti-correlation to correlation. So next, we consider the asymmetry parameter, which is the difference between the yard in the first and the third quadrants minus that in the second and the fourth quadrant, and divided by the sum of the total yard. You can see that the interference effect will give rise to anticorrelation in spite of intensity, but tabulation will give rise to correlation. After we consider both effects, there's a transition from the negative, from the anti-correlation to correlation. And for neon, we also did some calculation, but we didn't observe this kind of transition, which is good agreement with the experiment. Also, we can know there's also many semiclassical simulations on this topic, which shows that this transition can also be reproduced, and they can be attributed to the multiple rescattering events, and also Coulomb potential play important role in this process. Then we look at the post-lens effect. The Gatchen's group report a very interesting result for this low intensity with this correlation distribution will transist from a cross shape to anti-correlation when the pulse length increase from 4 femtosecond to 30 femtosecond. Colors group did very interesting works. They considered 6 different channels, and with careful consideration of the weight and phase of these different channels, they can successfully reproduce the experimental observation. That is a transition from the cross to anti-correlation. Here, they considered include the electron distinguishability and the intracycle events and different channels interference effect. For classical or the semiclassical result, there's also many effort. Gatchen's group also present some result in this paper. They use a semiclassical calculation, of course, with the specific scattering angle to reproduce their experimental result. And in this result from the Peixiang Lu's group, they use classical calculation. However, seems they cannot reproduce well the cross shape in the correlation distribution. So the next we consider how to improve our quantum model. It's well known that the Coulomb potential is ignored in the SFA model. For example, for these calculations, this is SFA result, and it's high intensity with 1 parawatt per square, and the distribution focus in near the orange, but for Semiclassical calculation, distribution is far from the orange, but that momentum is well consistent with the experiment. Analysis shows that in the SFA model, the multiple return is largely underestimated because of Coulomb focusing effect. These multiple return trajectories will play a very important role in the process. So how to incorporate this Coulomb potential in this model? Here's I would like to show some result. We consider the transition matrix to become composed of three parts. The first part is the turning and the subsequent evolution of the electron. We use the QTMC method. For the second one, we consider the quantum process of the excitation. And for the third, analyzing of the excited states, we use the Coulomb corrected SFA to take into account the Coulomb potential. Here's some result. We consider the first excited state since the intensity is low. So we think this one excited is this state should play the most important role. We can clearly see a transition of the shape from a cross to an anti-correlation. We also calculate this ratio between the anti-correlation and correlation. So this increase with the pulse length and saturated. It is in good agreement with experiment. So why this transition occurs? It can be attributed to the different contribution from the first return and the third return, which shows different distributions in the correlation distribution. The first return result shows that this is a cross shape. This shape depends on the competition between the residual momentum of the electron and the vector potential at collision. For the third return, distribution is anti-correlation. So when the pulse duration increases, we can see the transition from the cross to anti-correlation. So actually we can see there's no conclusion for this interference effect, for this pulse length dependent effect. Next, we go to the long wavelength result. This is experimental result from Xiaojun group for xenon with 2.4 micrometer laser field. This correlation distribution shows a very typical correlation. Most distribution are in the first and third quadrants. To show some detail or the quantitatively result, we calculate this asymmetry parameter again. We can see these fast oscillations in this intensity dependence of this parameter. At first, we also did some semiclassical simulation, which shows a smooth curve in this intensity dependence of the asymmetry parameter. There's some oscillations, small oscillations. This is due to the fluctuation in the Monte Carlo calculation method. Then we calculate the model, quantum model. We can see for these two channels, when we coherent sum them, we can see the symmetry broken and the interference effect appears. When we only consider the shortest pair or the first return trajectories, you can see for the rescattering impact analysis channel, there's no oscillations. But for this reside channel, we can see clear oscillations in the asymmetry parameters. However, this period of the oscillation is still much larger than experimental observations. Then we consider the different return trajectories, and the calculation shows that the first one and the third returns play the dominant role. So we calculate their contributions. We can see the asymmetry parameter indeed shows is faster oscillations when we consider the interference between the different return trajectories, this one as well. And when we make the sum of these two channels, we can observe this overall shape is in agreement with previous result, and we can also see this kind of fast oscillation with period in good agreement with the experiment observations. Okay, then this is not, of course, the end of the story. We still have many experimental results actually. If we look closely at the correlation distribution, we can see this small range distribution is very sensitive to the intensity. And we can see some particularly in these distributions. Next, when we consider the rescattering impact analysis process. We considered the electron return with the maximum kinetic energy, which is equal to 3.17 UP, as we all know. This is the energy conservation relationship among the collision. So the residual energy is shared by two electrons. If one electron takes no energy, then this one takes all the residual energy. If we consider the momentum of the two electrons, to consider the shift of the electron vector potential, we see that for this high energy electron is distributed in a specific surface in the momentum space. Here's some experimental result. We can see if we extract the data from this circle, then we can see that actually we got the Anderson cross section of this E to E process from the experiment. Here's some result for the xenon and argon for two different intensities. We extracted this cross section from this circle, and this is the result. You can see some very pronounced figure in these curves. All of them shows the maximum at 180 degree, and it decrease with decrease the angle, and with increased intensity, it will decrease faster and reach the minimum at about 120 to 140 degrees. We use the distorted waveform observation to simulate this E to E process. You can see that the result will produce the experiment date. So how to explain these figures? Actually, this cross-section structure is very similar to the elastic scattering, which shows also this kind of oscillations, and the maximum at 180 degree is called the Ramsey-Townsend diffraction effect. Let's consider the two trajectories typically. One electron moves around the nuclear clockwise, and the other one moves the anti-clockwise. Then they will interference with each other if they have the same final momentum. If the scattering is 180 degrees, obviously they have the same phase, so it interference constructively, typically, to get its maximum at 100 degrees. So when the angle decreases, there's a phase difference, then this curve will decrease until it reaches a minimum. Okay, based on this observation, we can propose a laser-induced inelastic diffraction method to image the ultra-fast dynamics of atoms, especially for molecules, which is very similar to the laser-induced elastic diffraction method, which has being already widely applied. We also use semiclassical model and quantum model try to reproduce the experimental observation. However, they both failed. Now, this is easy to be understood since here we only consider the Coulomb potential in this quantum model. We know that the scattering upon the Coulomb potential cannot be larger than the 180 degree. So we need to reconsider the short range potential more accurately. Okay, then the conclusion, like we showed before, interference effect still remains to be explored in the non-sequential tabulation processes. There are still only debates on this kind of processes, and new imaging technique can be developed based on the interference effect. And finally, our series still need to develop. Finally, I would like to acknowledge the many from the National Nature Science Foundation and National Basic Research Program of China and key program for science and technology research and project. Thank you for attention.
Thank you very much for your talk, very interesting talk. We have time for some questions, and we would like to ask everyone if they can send their questions through the Zoom applications, or you can also do by the Slack applications. So maybe in the meantime that we receive some questions, I can ask you one, which is I think basically just I don't know if you answer the question that you posed yourself. Could interference effects could be seen in a classical model? I don't know if I understood you well, that you have a full answer for that.
No, I don't think it can be observed in the classical, semi-classical, of course. So we are looking for some quantum effect, which is beyond the semi-classical or classical description of this process.
Okay. I'm trying to see whether there are some further questions here in the Zoom. I don't see any at this point, but maybe I can try to make one question related more on the new opportunities of these long wavelengths. I think you already show very well many of the things that have been observed in the near infrared lasers at 800 nanometers. But on top of that, now there are these mid-IR lasers. Then there will be several other effects, and you have mentioned some of them. For example, you haven't mentioned the importance of non-dipole effects. Or for example, I think you mentioned briefly about these multiple collisions being important. So could you comment more on the challenges that will arise when there will be more and more experiments on mid-IR lasers in these systems?
I mean for long wavelengths. Yeah, it's some kind of let me see, more related to for long wavelengths. Usually the UP is large, even for some even low intensity, right? So the kinetic energy of the return electron is very large. So this ionization or rescattering impact, I mean E to E process is usually important. So so far we think it's not so easy to find this kind of interference effect in this E to E process, because most important contribution is from the continuum states, so they are mixed together, especially in this Coulomb measurement. The statistic is usually low, so it's hard for you to find some subtle structures. But it's better maybe to find this interference effect in the recite channel, I think. But it is not, we don't need this kind of long wavelengths.
I see. Okay, I am checking here in the Zoom, and I don't see any other question at the moment. I don't know in the Slack channel.
I see one from Nakala.
Okay, please go ahead.
So my question is related to your model, including the Coulomb potential. Thank you so much for pointing out that quantum interference is important, first of all, in some regimes of NSGI. And second, I realized that so far you have done only a single channel contribution, but we both know that interchannel interference can be important. So do you intend to extend your model to that? And have you done any comparisons?
Yeah, we are considering that is important. In fact, as I mentioned in the talk, for this low intensity, it's about 100 terawatts per square meter. So we think this first excitation state should be the most important one. And you can see that even with this single channel, we can reproduce qualitatively this experimental observation. That means here maybe the interference effect may not be important. Of course, your suggestion, of course, is very important. We are doing these kind of calculations to look at the interchannel interference and also other relative effect. Thank you.
Thank you. Also, one question I would have is, what, in your opinion, is more important in this regime, quantum interference or the role of the Coulomb potential? Because we know both break the fourfold symmetry you get with the strong field approximation. But it's a difficult question. Which one would play a more important role?
It's good, and as you said, difficult question. It depends, I think. If, for example, as you mentioned, for higher intensity, I think if more channels are involved, the interference will be important. Of course, it's hard to say which one is more important.